Swayam Prabha. Digital India. Educated India.
So you see that, that's my test. I put P1, P2, P3, P4 in this matrix, and the fourth column is all ones, and then I calculate the determinant of this matrix. And it turns out to be negative. P4 is outside. If it's positive, P4 is inside, and that's my in-circle test. So I need this during construction of a Delaunay triangulation. There is a variant of the constraint of the Delaunay triangulation known as the constrained Delaunay triangulation. So a constrained Delaunay triangulation is a triangulation with, the set of sides P and an additional constraint that you want certain edges to be present in the triangulation. Now, if you are imposing this constraint, those edges may not be Delaunay edges. That is, they may violate the Delaunay criterion. So, two things. Constraint edges need not be Delaunay. So it's not, the triangulation is no more Delaunay in that sense. That is, not all triangles will satisfy the empty circle criterion. And all Delaunay edges that do not cross the interior of any of these constraint edges belong to the CDT. That is to say that intersecting Delaunay edges are not part of this triangulation, because it has to respect the constraints. So let's take a look at this example where you have this points and edges as input, the guitar on the left hand side, and the points are used to construct a Delaunay triangulation. In the second case, I'll try to move my cursor over here. The second one is a Delaunay triangulation. So notice that the edges of the guitar in the input are ignored. We do not impose any constraint. So for example, you can see that the handle is not present here, and that's my Delaunay, the usual Delaunay triangulation, and all the triangles satisfy the Delaunay criteria. In the third case, I have a CDT where I impose the Delaunay, the constraint edges from the input. So you see that the edges from the guitar handle can be seen. You can make out the edges in that, and that is my CDT, or the constrained Delaunay triangulation. And from the CDT, if I remove the concavities, I get a CDT without concavities. In that case, the boundary of my CDT looks like that of a guitar. And then on top of that, I can introduce extra vertices, and those vertices, otherwise known as Steiner vertices, will improve the quality of the triangulation. But while improving the quality, I might have to split the constraint edges, right? So in a real sense, that's a modification of the CDT, but you might want that sometimes. So that's my CDT, constraint Delaunay triangulation. Okay, so that's Delaunay triangulation and constraint Delaunay triangulation. Let's come to the dual of Delaunay triangulation, which is again a very well-known data structure. In fact, a very powerful data structure. And given a set of sites, be a set of points in RD space, we associate to each site Pi its Voronoi region, VPI, and the relationship is, the definition of the Voronoi region Pi is that any point in the plane that belongs to the Voronoi region is closer to Pi than it is to any other point. So maybe it's best to describe that with an illustration. Right. So Voronoi region. So let's say in this, I draw the sites in red here, and I take a very two-dimensional example. Any point here, and let's call them P0 and P1. Any point Q here. So there are two regions, two Voronoi regions in this case, Voronoi region V0 and Voronoi region V1. And those are defined by splitting the entire plane by a bisector of P0 and P1. And the property that Q is closer to P1 than it is to P0. So the Voronoi region of Q is V1.
Or just so your screen is not visible. Yeah, your screen is what you're writing on the white screen is not visible. Can you just?
It's not visible.
Yeah.
It's visible to me.
Yeah, it's visible to me as well.
Okay. So maybe I'll just refresh and see. Okay.
Yeah, I think it's also visible to me because I'm logged into two devices. I can see that.
Okay.
I can see it on the other.
Okay, you carry on then. Yeah.
Right. So okay. So basically you have these two Voronoi regions, and then the Voronoi region V1 has this property that all the points in that region have P1 as its seed point, you could say. Every point is closer to P1 than it is to P0. Right? That's the case with two points. And let me extend that and generalize it a little bit. So let's say I have multiple points, and that's another Voronoi diagram I'm gonna draw now. And so Voronoi diagram, when you want to draw Voronoi diagram of points, you just take bisectors and collect them as a partition of the plane. So it will result in some convex polygons, and some of those convex polygons may be infinite. So if I draw, and I'm trying to draw it by taking pairwise bisectors of these points. That's one nice recipe to build a Voronoi diagram by hand. I'm just drawing these bisectors, and then some point of time I need to sort of draw the interior ones as well. And let me see if I can do it. Okay, I think I'm successful in drawing the Voronoi diagram. Okay, so that's my Voronoi diagram here, and then so in this case it so happens that all the tiles are infinite, but let me introduce one more red point here and make the tiles, at least one tile, finite. Yeah. So that's my Voronoi diagram. And if I consider any tile, let's say the central tile here, any point in this tile is closer to its seed or its generator point than it is to any other. So in that sense, this distance is shortest among all the distances. That's the property of a Voronoi diagram. So that's the Voronoi tile. And this is what I wrote on that slide. Let's go back to that. Right. So we associate to each side Pi its Voronoi region VPI, such that any point in that Voronoi region is closer to Pi than it is to any other seed point. I hope that is clear now. Any quick questions on that? All right. So So these are Voronoi regions. What is a Voronoi diagram? The Voronoi diagram is a collection of non-empty Voronoi regions and their faces together with their incidence relationships, right? So the tiles and then the boundaries of these tiles together form the Voronoi diagram. Right. The Voronoi diagram of right. So this I already told you guys. Any point in RD belongs to at least one Voronoi region, and the locus of points equidistant to sites Pi and Pj is the bisector, right? So between two points, the line that goes exactly in between is the bisector, and that belongs to the it belongs to the boundary of a Voronoi cell or a Voronoi region. All Voronoi cells are convex by definition. They can't be concave because they are. Okay, that's a good question. Who will tell me why are Voronoi? So you have seen the construction of Voronoi regions. That is, you draw bisectors and then take intersection of the half spaces. Who would tell me that why the Voronoi cells are necessarily convex? They may be infinite, but they're always convex. They're never concave. Who would tell me why is that so? Anybody?
They are like, say, they can be like, they are all the vertices of a Voronoi cell can be like, say, considered to be equidistant from the particular Voronoi point assigned to it, we can say. If we
Yes, but
yeah,
what does this tell about convexity?
So in that sense, if they are all equidistant, then we can say that we can draw the so that is a circumcircle which can be drawn, and that will like say that we can all have triangles which will have circumcircles drawn like that, and those triangles will can be made only in a convex shape.
So wait, I think I lost you somewhere in between. Where are these triangles coming from?
Okay, so like if we join that point to each to like all of the vertices, we'll get some n triangles depending on how many sides the
But
particular shape
I can
is.
have more. I can have something else other than triangles if I'm joining. I mean, how exactly are you joining these points to make triangles? I think there is a simpler answer that I'm looking for.
Okay.
So, I mean, the answer is in my question. I said that by construction, the Voronoi diagram, you construct it by taking intersections of half spaces. And when you take intersections of half spaces, you always get a convex region. Full stop. So you can't take intersections of half spaces and construct a concave space. Okay, think about that anyway. But what you have said might be correct. There are alternate deductions possible, but I didn't really fully get what you were saying. Maybe because it's best drawn. So excuse me if I didn't understand your response. But a simple answer to that is intersection of half spaces will always give you convex regions, and you can try it out yourself as well. Right? Split the space and consider a lot of half spaces, you'll get that.
Yes.
Okay, so let's see the Voronoi triangulation. How does it relate to the Delaunay triangulation? The Delaunay triangulation is the dual to the Voronoi diagram. And what do I mean by a dual? Let me very quickly explain what I mean by a dual of a triangulation. And I think that idea will probably be useful when I'm looking at that. So dual graph, right? So a dual graph. So both the Delaunay triangulation and Voronoi diagram are graphs. A dual graph, let's start with a triangulation, and what I'm drawing is not necessarily a Delaunay, but we are discussing this in context of Delaunay. So I'm drawing a primal graph here, a primal or a primary graph. It's called a primal graph here. Let the primal graph be a triangulation, and because we are discussing Delaunay and Voronoi, let it be a Delaunay triangulation. So in a primal graph, and then you have a dual graph. An edge in a primal graph transforms to an edge in a dual graph, and vice versa. A point in a primal graph becomes a facet in a dual graph, and a facet in a primal graph transforms to a point in a dual graph. So let's see how it looks like. Let me draw in red the dual of it. So every edge becomes a dual edge. I'm drawing all the edges here. Sorry, this goes to infinity. And you will quickly see why the Voronoi, how the Voronoi is related to. See, I very quickly could draw the Voronoi diagram here because I had the Delaunay triangulation. So you would notice that every Delaunay edge has a corresponding dual Voronoi edge. Every facet, every triangle has a Voronoi vertex, and every triangle vertex has a corresponding Voronoi facet. This is the primal dual relationship. I can always go from, given a dual graph, I can go to the primal graph. Given a primal graph, I can go to the dual graph. So that's just a quick discussion on primal and dual. So in our case, the Delaunay is dual to the Voronoi diagram, and it's very easy to go back and forth between them. Now, how do we write? So in 2D, each triangle PQR is dual to the Voronoi vertex, where these three regions VP, VQ, and VR meet, right? So there's a small illustration that I made here, which is exactly what I had drawn on that screen. But I hope this is clear, right? So you have these VP, VQ, and VR. These are, let's say, these are the three adjacent facets, and then the Voronoi vertices of VP, VQ, VR will form a Delaunay triangle, right? So I hope I haven't confused you, but if you just remember that primal dual diagram, it should be clear. Does anybody have any question on this primal dual relationship? Okay, then I think we are good to go. So right, so talking more about Voronoi diagrams, we have seen the Voronoi diagram of between point and point, a point and point. So basically, we just need to know the bisectors between these primitives. So between point and point, the bisector of point and point is a line. The bisector of a point and segment is a, who will tell me what is this central red guy here? The bisector between a point and a line.
A parabola.
It is. Oh, wonderful! It's a parabola. So why do you think it's a parabola? It could be a circular arc or a hyperbola or whatever.
Because a parabola is defined that way.
Sorry, parabola is
locus, defined as a locus between which is like bisecting a point and a line.
Yes, very nice, great. So you have this point, which is the focus of the parabola, and this line serves as the directrix You guys remember the directrix? And
Yes,
a
yes.
parabola is defined as a locus such that the distance between the parabola from this focus and the perpendicular distance between the foot and or to the directrix are the same. So essentially, in layman language, this parabola is a bisector between segment and point. Okay, and then between segment, the bisector is a straight line again, right? So below here, I have some Voronoi diagrams of non-point primitives. If you have three disconnected lines, you could then imagine that a line is made up of a line segment is considered as a line segment in a finite line segment, and 2 points at the ends, right? So when you want to construct a Voronoi diagram of discrete set of lines disconnected, then you have to consider the Voronoi diagram between line and point point. All of these cases will happen. So the Voronoi diagram on the left will have straight lines and parabolic parts, as you can see here. Okay. On the right hand side, you see a closed polygon. It's a concave polygon, and that's on purpose to show you what a concave polygon, the Voronoi diagram will look like. In that case, you have it mainly consists of straight lines because you have these line bisectors. But wherever there is a concavity, you have to consider that point as a point, not as a line, and then that will have some parabolic arcs. Do we need to do some illustrations here, or this is fine? We can stop here because this is something extra. Usually you would encounter a point Voronoi diagram of points, but it's interesting to see how the Voronoi diagram of higher order primitives look like. And then you can have Voronoi diagram of circles and parabolas, hyperbolas, and so on. But the main idea remains the same: is that you would want to be able to create bisectors, and then that forms the basis of creating a Voronoi diagram. Any quick questions before we start?
Yes, sir. Sir, what if we have 4 points and these 4 points are the corner of the square? Then the Voronoi diagram will be a yes.
Yeah, so that's a pathological case. Usually what happens, and then I can show it to you. In this example, you can see that look at the Voronoi. Okay, do we have a better? Maybe this one. So if you have a Voronoi diagram, if you have a Voronoi diagram, then you will have a Voronoi vertex that is intersection of 3 Voronoi regions. So you have 3 Voronoi regions and then the intersection. And when you have 4, and look at the dual of those 3 vertices. Those 3 vertices then form a triangle in the Delaunay triangulation. So that Voronoi vertex is the circumcenter of the triangle of the Delaunay triangulation. Do I need to draw, or you can visualize that? Right. So
Yes.
think of 3 points in space. These 3 points in space will have their own Voronoi regions, and these 3 Voronoi regions will meet at a point. That point is the Voronoi vertex. And this Voronoi vertex, by whatever definitions we have covered so far, is the circumcenter of the Delaunay triangulation, the dual Delaunay triangulation that connects these 3 points and forms a triangle. Okay. So now coming to your question, it's a very good question. What if I have 4, and I will extend your question. You said it belongs to a square or a rectangle, but let me extend that question. That what if these 4 points are co-circular? That is, these 4 points lie on a circle. In that case, this is a sort of a pathological case, because in this case, what happens that those four regions, the four Voronoi regions, will intersect at a point. This would not usually happen, but in case 4 points become co-circular, this will happen, or 4 or more points become co-circular, this will happen. See, 3 points will always be co-circular, but if 4 or more points become co-circular, then we will have a Voronoi vertex there. And then what will happen to the Delaunay triangulation? The Delaunay triangulation, I have a choice to make this is an ambiguous case, because I can flip the triangles. I can have let's come back to the square case. I can have 2 triangles, but then the other 2 triangles with the different diagonal can also be Delaunay. So that's the pathology in this case. But I hope I answered your question. Is that you will still have one
Yes.
Voronoi vertex there, but this is not the usual case.
Okay, sir.
Okay, but that can happen. That can happen very easily. And a very classical, I can give you a classical example is, take a circle and take n points on the circle and try to create its Voronoi diagram. What you get is a set of spokes connecting the center of the circle. That's the Voronoi diagram of the circle. Right?
Yes, sir. Yes,
Yeah.
sir.
So that's a pathological case. Anyway, so that was Voronoi diagram. And right. So there is a related concept when it comes to Voronoi diagrams. A medial axis of a shape, and then there is a very close relationship between medial axis and the Voronoi diagram. Is a medial axis represents a set of primitives that define the center of a shape. That's informal. Okay. But formally, the medial axis is the locus of center of all maximum balls. So let's say we have this shape here on the right, and I can define disks inside this shape. If I expand that disk to the extent that it touches 2 or more points on the boundary of the shape, that disk or a ball is known as a maximal ball. Okay, so a medial axis is then defined as, and it touches the shape tangentially, right? So you can see that I have drawn a lot of circles here that are maximal balls. So all of these balls touch the shape tangentially at 2 or more points, and the medial axis is then defined as the locus of the center of all maximal balls, right? Does that make sense? Do you? And then I will tell you what's the relationship here. But does that sort of right? So I connect the centers of these maximal balls, and that gives me a medial axis. So a medial axis for a 2D shape consists of curves, and those curves are connected, forms a tree-like structure, like you can see here. And there are 2 types of it is also known by certain other names. You could also say skeleton of the shape, or a medial axis. Medial axis is I would say a more technical, a term that is more appropriate to use, but skeleton is also used informally. The endoskeleton is the skeleton inside, the exoskeleton is the skeleton outside of the shape, right? So that's the definition of a medial axis. Now the Voronoi diagram, because it is defined using the bisectors, can be used to approximate the medial axis. Medial axis is a very well-known structure in geometry, the Voronoi diagram can be used to approximate medial axis, because by construction Voronoi diagram takes the bisectors of the primitives, right?